Hi, and welcome to What the Fuzz. We are Cornelius Aschermann, that's me, and I'm currently a researcher at Ruhr-Universität Bochum, and I'm mostly focusing on program analysis and automated bug finding, and I also occasionally work as a security consultant. And with me here is Sergej Schumilo, who is also a researcher at Ruhr-Universität Bochum, and who likewise focuses on bug finding, and in particular, he's very interested in everything low level. So what do we care about? We care about finding bugs, and we believe that manual analysis doesn't scale too well. So we would like to have some kind of automated tooling. And there's a whole bunch of fields that try to build all kinds of tools. For example, the verification field. But yeah, so no, just no. So we do fuzzing because fuzzing actually works. And what's a fuzzer? Typically we consider, like a whole bunch of people consider fuzzers black boxes with some kind of magic content where you put in a program and you obtain bugs for free. So there's a whole bunch of other people that are basically like, but fuzzers is pretty dumb. We tried this in the 80s, it didn't work. And I would like to disagree with that, and we would like to show a very short demo where we modified a Super Mario game in such a way that a modern fuzzer can play Super Mario. And what you get if you do that is actually pretty impressive, I think. So here we go. So I don't know if you can hear that, but like that thing plays Super Mario a lot better than I do. And we even made this game harder by killing Mario every time he gets stuck. So he's basically forced to run the whole time, and he must never get stuck anywhere, or we kill him immediately. Right, so I don't know. You can come here and play Super Mario if you want later, but I'd wager there's not that many people that can play Super Mario at this level. Okay, so that said, fuzzers are still dumb. So if you think fuzzers are dumb, you're not wrong. In particular, if we, like this is a plot of all the different things the fuzzer tried when solving such a level. In particular, in the beginning, we see that the fuzzer tries a lot of very dumb stuff. He's mostly dying in the first trench he can fall into. However, modern fuzzers are learning how to trigger interesting behavior in the target application, and as the fuzzer progresses, there's really no way in jumping into the ditch over and over again because it does not yield interesting behavior. So the only option the fuzzer has to expand forward is to expand forward. And eventually, towards the end of the level, the only real thing the fuzzer can do is progress in the level. And in this case, the level took us, our fuzzer, something like 8 minutes to solve. All right, so how does the fuzzer actually learn what's interesting behavior and what's not? So we have a target application, and usually we assume we have some kind of seed input. In these examples, we typically just used an empty seed input. You can use empty or a set of A's, or you might just use actually reasonable seed inputs, whatever you have available. And the fuzzer creates some mutations of the seed inputs, puts them into the target program so the target program can run, and observes the coverage that is created by these inputs. And if there was a new coverage triggered, then this input is stored in the queue and will be used for future mutations. And if there's no new coverage triggered, such as in this case, then the input is immediately discarded. And using this, the fuzzer can iteratively build a corpus of better and better test cases that trigger new interesting behavior. So basically, the current thought on fuzzers is that fuzzers are artificial intelligences for test case generation. And in this talk, we'd like to challenge that belief a bit. So the key takeaway so far is, like if you have seen the Google talk or any other of the results, fuzzers are amazingly at smashing bugs. Like they are bug killing machines unlike anything else. And if you're not using them, someone else will be using them on your software. So, and they might not have your best interest in mind when they do that. So the rest of the,
Yeah, thank you. So, well, the rest of this talk, basically, we'll talk about our past research, and later on, Cornelius will continue with basically the future of fuzzing. And, well, 2 years ago, when we started our fuzzing journey, our research, well, yeah, let me derail a bit. So basically, what we wanted to build is something like, so during the Cold War, some engineers in the Eastern Bloc thought it would be a good idea to put MiG jet engines on top of a T-34 tank chassis. And well, there's just one purpose for this monstrosity, is just to blow out fires like burning oil fields, so serious stuff. And we want to build something which has the same characteristics, but as a fuzzer. Okay, so since a fuzzer, or since this monstrosity does not care whether an application is compiled or written in a specific programming language, we don't care either. So basically, we will focus on binary-only fuzzing. So we just care at the executable itself. If it is x86, we can just fuzz it, and we're good to go. And next, basically, there are different platforms, so different OS-specific interfaces and different ways to obtain runtime information, so coverage, basically, on different operating systems. And yeah, same. We just don't care. We want to fuzz them all. And yeah, the same goes for the different privilege levels. So we want to fuzz ring tree applications, so user space applications. We want to fuzz targets in kernel land, in ring 0, and even in ring -1. So we want to test hypervisors and UFI. So they're cool stuff, basically. And yeah, actually, we just want to steamroll over all privilege levels with our approach. And yeah, this is basically the reason why we started to build our own fuzzing framework 3 years ago. Well, it is known under the name Nyx, and basically the name is based on Greek mythology. And yeah, it's referring to the daughter of chaos and the goddess of the night. So some parts of our fuzzing framework are already available and released on GitHub under the name of KFL, Red Queen, Grimoire, and Nautilus. So at the last slide, we will, there are multiple links to our GitHub repos. But let us talk a little bit about the architecture of a common coverage-guided fuzzer like AFL, for instance. So basically, there's a target and a fuzzer, and the fuzzer has multiple modules. So a coverage measuring module, so that we can measure runtime information, and an input generator, which generates inputs and provides the inputs to the target. And later on, the input is consumed by the target, and the target provides the coverage information to the fuzzer. Easy, right? But what if we apply this approach to a target in kernel land? Well, yeah, it's not as easy as it might seem. So it really depends on the operating systems, but sometimes it's just hell to get runtime information from a kernel target. And there's another issue. So fuzzers are really good at finding bugs. And in kernel land, there are bugs, right? So what will happen if this fuzzer will find a bug? So basically, the fuzzer will basically kill its own hosting operating system. So you can fix this issue basically by putting everything into a virtual machine. And in case of crashes and blue screens, you can just reset everything and you are good to go. Simple, right? So if you run your target in a virtual machine, there are just multiple benefits. So for instance, fault tolerance for free. Then you can also scale. You can just launch multiple operating systems and run them on one single machine. So in theory, it's simple. We got our target, which runs in a virtual machine, and we scale. But in practice, well, there's another kind of architecture. So in between, we use a software component called agent. And the agent communicates somehow with our fuzzer, which runs at hypervisor level, and expects data from the fuzzer, and then provides it to the target and somehow we will obtain runtime information. And by using this modular architecture, you can just write agent for basically anything. So you can write agents for kernel targets, user space targets, or even hypervisors. Just think about it. So if you just put agent code into a custom operating system, custom operating system, you can basically run a custom agent OS inside of your target hypervisor you want to test in our hypervisor. So by using,
Actually, let me interrupt there for a second, because before we go over to coverage fuzzing this, we actually built this agent. And so we built a custom operating system that runs inside of a hypervisor and tries to misbehave as much as possible. And since we didn't have coverage in this test setup, we actually ran it without any coverage. So back to the 80s dump fuzzing, right? So just generating random interactions and running them. And to our big surprise, it turns out this crashes pretty much all of the hypervisors. So
yeah, we were able to uncover up to 50 different bugs and I guess 40 CVEs assigned.
Something like that.
Something
yes.
like that. So yeah, but do we have a demo or?
Yeah. Actually, I think we can demo that.
Okay.
Yeah. So since this is 80s technology, we actually brought some 80s technology where this is stored.
Yeah, and I guess it's the same superior technology as this guy shows us, right?
Yeah. So we actually have this USB. Floppy disk drive here. I'm the kind of generation that hardly ever used floppy disks, so we try to put this in here. All right. So now we have to make the floppy disk available because we don't want to run QEMU in root mode for this demo, for obvious reasons. And then we can run QEMU and make it boot from the floppy disk. So this floppy disk, like the boot process is pretty slow, but that's because of the floppy disk. If you run this operating system from somewhere,
it just takes a couple of milliseconds.
Yes. So it's still copying all the stuff from the floppy disk. And this QEMU is actually the latest checkout. We checked out the nightly build yesterday. And so you can see the operating system booting. And then we'll start fuzzing very soon. And you can see, whoa, that went quick. Like fuzzing is supposed to take longer, right? Like fuzzing is supposed to take a day or two or something like that. But it's really more like a few seconds. And if you actually, like this fuzzer was limited to the VGA stuff, if you fuzz the whole system, it will even go faster. So yes, that's how far you can get with not even coverage fuzzing. And we don't really know why that's the case. Apparently no one really ever made the effort.
Yeah, so do we need this copy or?
No, actually, I don't think we need this anymore.
Okay, so maybe.
Does anyone want this? All right. So the rest of you, sorry, will have to wait until mid next year. So then we'll release all of that. Okay. So sorry for the interruption. And
yeah, sure. Yeah, as I already mentioned it, you can basically put everything into a virtual machine to trace a virtual machine. And basically, by using this approach, we are, to the best of our knowledge, the first who tried to build a coverage-guided hypervisor fuzzer. So this was dump fuzzing, and later next year, we are expecting even more results using coverage-guided hypervisor fuzzing. So, I talked a lot about the architecture, the agents, and well, the interesting part is how we obtain coverage information. And well, for this purpose, we rely on a technology called Intel PT, and I'm pretty sure that some of you have already heard about it. It stands for Intel Processor Trace, and Intel PT basically provides the ability to the CPU to basically trace itself and write trace data directly to physical memory. And if you can also provide the program which has been traced, which has been executed during runtime, we can just put both into an Intel PT decoder, and you will get a list of addresses executed. And since we are at hypervisor level, it's actually pretty easy to just dump memory, so it's not a big task. So And yeah, later on, we can just translate traces to transitions, and then we will get something like a bitmap representation. It's basically the same as AFL does. So, yeah, just let us take a look at all the different components and the communication for one iteration. So we got our fuzzer. Our fuzzer has access to our modified hypervisor, so QEMU in ring 3, and KVM in ring 0, and in the virtual machine, an agent in the user space, and a target in the kernel. And, well, at some point, the agent will signal that it's ready to receive data, and we then just generate a new payload and write the payload directly to the guest's physical memory, and then continue the execution, and the data is in the physical memory, so the agent can just pass the payload to the target. At the same time, we will trace the target using Intel PT, and that's basically it. So this is how an iteration in our framework works. And by doing so, we can trace everything, at least. So it has to be x86, but that's it. So, and using this approach, yeah, so we've benchmarked our framework against AFL. And as you can see, sometimes our approach is faster, sometimes AFL is. But you have to consider that AFL is a fuzzer which needs or which relies on compile time instrumentation. So you need the source code. And our approach is binary only. We don't care. And as you can see, so to the best of our knowledge, this is by far the fastest binary only fuzzer out there. So actually, fast binary fuzzing is awesome. And yeah, we basically want to improve it. And there's one more thing. So you can go even faster. And to do so, we've implemented a technique or a mechanism in our hypervisor called fast VM reloads. And those fast VM reloads, in theory, you're able to reload a virtual machine up to 6,000 times per second on a single core. And well, by doing so, I will come to this in a minute, there are multiple advantages. But first of all, to implement this mechanism, first of all, you have to deal with the internal state of QEMU, and QEMU on each VM snapshot reload, yeah, just does multiple very expensive calls to expensive methods to restore state. And instead of just walking over a tree and calling expensive methods, we just put everything into a list of addresses and just memcopy it, and we're good to go. It's super fast. And yeah, instead of just reloading the entire guest memory, we just keep track of all dirty addresses during one iteration, and then we can just iterate over the stack and just fix the dirty pages. Easy, right? And how do we deal with emulated hard disks? Basically, we implemented our own layer on top of it. So during each iteration, when the guest tries to access the hard disk, we just intercept and put everything in our copy on write cache. And well, to reset everything, we just have to forget the cache. And that's it. And well, by doing so, let me show you some performance numbers. So we picked the GDI plus test exe from WinAFL, and well, the raw numbers to just execute this executable in a loop, well, you're able to achieve up to 80 executions per second. Windows is quite slow.
So that's without any kind of fuzzer or instrumentation or anything, right?
Yeah.
It's just starting the program and waiting for it.
Yeah, so this is basically the upper limit. And then you want to write files, right? You need to provide payloads. Then the execution will drop. But fortunately, we got VM reloads, and we don't care about process creation. And as you can see, you can improve performance up to 145 executions per second, combining Intel PT tracing, full trace decoding, file writes, and so on. So, to summarize, we can reset an entire virtual machine and trace our guest faster than Windows is able to create one process. So, snapshots. If you use them, you can avoid startup time, and you don't have to suffer from noise bugs and other non-determinism issues. And there is no statefulness. So basically, if you try to fuzz something like bash, bash actually will fuck up your entire the entire file system by just writing and deleting files. If you fuzz bash, right? By using full VM reloads, it's just gone. And of course, we found multiple bugs using our approach. So here's our trophy case. We found bugs in macOS and QEMU and in Counter-Strike Source and different programming languages and so on. So not a big task, right? If you combine just the latest tech and use it for your fuzzing purposes. So,
all right. So thanks for all the technical details. And I think we really can see that it's basically possible to build a fuzzer that is able to fuzz pretty much everything. For the rest of this talk, we will talk about what we think. So basically, we will be finishing our PhD within the next few months, and we spend a lot of time researching. I think with our colleagues, it's about 10 person years or something like that of fuzzing research. And we would like to share some ideas on how the future of fuzzing research might look like. And of course, we're going to look into a crystal ball here a bit, but I hope we can draw a map on interesting areas for future research. Because every new colleague that starts has this tendency trying to optimize the mutator or trying to optimize the scheduling algorithm of fuzzers. And I've been there too. Like when I started, I did that too, and turns out that's not a very good idea. So the most important thing that we need is harnessing. So harnessing is basically the process of making your software compatible with the fuzzer, which in many cases is quite painful. The current state is that if your software consumes a single file, then that's exactly the model all the current fuzzers are really good at. If it doesn't, it's a lot harder. To give you an example, when we were fuzzing Counter-Strike Source, we needed to combine our fuzzer with Counter-Strike Source and to create an agent that talks to Counter-Strike Source. And what we wanted to do was to fuzz the map loader. Now, we didn't care about the map loader of the server, we cared about the map loader of the client that receives the map from the server, because that would be interesting to exploit all the clients from the server. And we did that, and we were able to write such an interface, and that was the code for this interface. And that was about 2,000 lines of code, I think.
Yes.
And I mean, that works. So we spent 3 days writing the interface code, and then the fuzzer found a crash within the first few seconds. Now, that did not feel particularly satisfying. That ratio, we might as well have tried to look at the code ourselves. So I think there's ways to really increase the usability of fuzzers. For example, imagine a system where you have this ability to create a snapshot, and you run GDB. So you run GDB, you run the target, you set a breakpoint wherever, and you run the target, and it hits the breakpoint. And in that case, it's on calling receive on the network buffer that we care about. And then we just have all the information that we need to create or to spawn the fuzzer. We can tell the fuzzer, hey, this is where you need to store the size of the data that was produced by the fuzzer. This is what the maximum amount of data you can produce, and this is where you should store the data. And now go fuzz my target. And that's something that should exist, but currently does not, even though technically it's quite easily doable. And I think there's lots of more of these interface hacks that make fuzzers more accessible to projects that are currently not fuzzed. A similar issue is there's so many scenarios where you have multiple interacting modules. For example, in an SSHD, you have a privileged server and then underprivileged processes that are communicating with the network. You might have a browser where you have a browser process and underprivileged render process, or you might have a web server where you have a web server and a database and eventually some sub-processes for some heavy computation tasks. And in all those cases, we have all those clearly defined IPC interfaces or network interfaces. And it would be really neat if there was a tool that allowed you to basically hook into a full system and look at all the interfaces that are being used and then attack each component via the given interface. And there's been some research on that, in particular, for example, on libraries. There's been some pretty cool research where people were looking at how libraries are used by programs and then automatically create test harnesses based on existing library usage. So generally, I think the most important thing here is to improve the usability of fuzzers, to make it easier to use fuzzers on software that you cannot currently fuzz with the standard fuzzing approaches, such as AFL. As we said, for example, binary fuzzing is usually a lot easier to use than source code fuzzing because there might be some really weird build systems. And I don't know, who has dealt with like really weird build systems? I think that's, yeah. Right, that's not fun. Not fun at all. Trying to get like a Clang into this old code base that just doesn't compile with anything newer than GCC 2 or something, not fun. So the next thing is, we've been talking about these communicating systems, right? A lot of the fuzzers are currently just producing a single file. And if we're having interactive systems that consume data over time, we could profit heavily from having fuzzers that acknowledge this and that are able to create test scenarios that are more like a test book or test script or whatever, where, for example, to fuzz a kernel system, you create a whole series of interactions, and the fuzzer is aware of when each interaction actually triggers something in the kernel. There's something like that for file systems, but nothing general. And it would be really cool to have a more general way to express this kind of test scenarios. So you could use grammar fuzzing for this, which we did, but there's some downsides. You want to have binary data in there. You want to also have structured data in there. And you want to probably express certain types, certain type information, such as you can't use a file system after unmounting it, because if you do, the fuzzer will create a large amount of false positive inputs that are just crashing for the reason that you abused the target and not that you misused, like the target wasn't buggy, you just didn't stick to the invariance that the target expects. If we have such a system, so you remember the Super Mario demo, I assume. So when we start fuzzing a Super Mario level, we get like 200, 300 executions per second. But as Super Mario goes through the level, the input size grows, right? Like there's more interactions that Super Mario has to perform to get further into the level. As the input size grows, the fuzzer does not know where to mutate. So the deeper we get into the level, the less likely it is that the fuzzer actually mutates the part that we care about, which is the last few interactions. If we have explicit knowledge of the fact that certain parts of the input are not relevant, or they should not be changed, because if we change this message, then all of the rest of the messages is most likely not going to do anything useful. So we can really focus our mutations on the last few interactions. Now, if we combine this with the fast VM reloads that we talked about, we can make the Super Mario demo much faster, because as we get into fuzzing Super Mario, as Mario gets like deeper and deeper into the level, each individual run also takes more time, right? First of all, it's less likely that we mutate the right bytes, but secondly, each individual execution gets a lot slower. And in our case, that was like, we started out with 200 executions, and like after half the level, we're down to 10 executions per second. If we have a snapshot somewhere in the middle, and we know we'll only mutate the last few interactions, then we can cut away all the boot up time, which is also what gave us the big performance advantage over Windows, and create new fuzzing runs from this snapshot. Now, the snapshotting process is about as fast as the reloading process, so this is very cheap, and we can just do that for every input that we want to mutate. And that can actually save a lot of time.
Yeah, so basically a good example is Counter-Strike Source. It takes minutes to start a game, but we don't care. We just want to set up the memory and start at a particular point during execution. And
yeah, we don't want to wait for all the graphics libraries to load and all the files and all the assets being loaded. That's not something we want to do for each fuzzing iteration. And this would be massively helpful in a lot of different scenarios. For example, kernel testing. There's actually a tool that does a limited subset of this. It's called syscaller, and it's like, if you haven't seen the output statistics of syscaller, the link is down there. I'm not sure if you can read it on the presenter, but it's in the slides. If you haven't had a look at the output of syscaller, I can heavily recommend it. There was a page where all the open issues that syscaller automatically filed were available, and it was like 30 use after free vulnerabilities at every given day in the Linux kernel or something like that. Then you can use this for network protocol fuzzing, which is quite painful right now. You can use this to build much better web crawlers. Imagine you have a web crawler for your standard web application security issues that is combined with the feedback fuzzer. And now all of a sudden complex forms and all those kind of issues like authentication, login, logout, they're not really issues anymore because the feedback fuzzer generates test scenarios in which all these issues are solved. So what we need is, well, not actually bigger guns, but a better way to express specifications for how the target should be used. And that brings us to the next point. When you're using a fuzzer, you need to kind of understand what the target application is doing, because the model where you have a magic box where you put in a program and get out bugs, well, that works if your target has not gotten a lot of attention recently, as with our hypervisors. But in reality, it usually works more like you fuzz your target for a while, then you manually inspect the code coverage produced, and then you fix something on your fuzzing setup, and then you inspect the code coverage again, and eventually, after a few iterations, you will get a bug. And we're very dissatisfied with the current state of the tools available to inspect the process the fuzzer makes. So we built something. And I think this is an interesting area of further research, and I would like to demo this. So we have a small web interface. Don't try to hack me. I'm not online, even though this is listening to every connection. So we have this this interface. This is basically just your average. You can't really see the colors, I guess, but this is basically just your average code coverage tool that you already know. However, there's a few tricks to it. So first of all, we can add a fuzzing queue. Like usually you would watch a fuzzing directory to interactively add this, but as you can see, the coverage was computed very quickly. So I don't know who has used kcov and the like, but it's painfully slow. And this uses the same technology fuzzers use, like fork servers and all that, to calculate the coverage with a few thousand tests per second, or at least a few hundred tests per second. So you can use this interactively and actually watch your fuzzer progress through the program. There's also a whole bunch of other really neat issues or neat things you can do. First of all, you get the disassembly side by side with your code coverage, which is sometimes very relevant. But also we have all those trace information, right? We can use this trace information. So this tool is not aware of any programming language. This tool solemnly operates on binary data. So this code here is just parsing dwarf data and reading the file and inferring which code was covered. And we actually get this whole set of IDE-like features. So for example, we have a call here, and we can see that this call went to this line because we have the trace data. So we can do goto or xrefs based on the live trace data. And similarly, if we're in some function and we don't know how we got there, we can just say, hey, where did the returns go to? So we see all the instances where memcopy was used. You can also, for example, inspect the individual test cases that got you to this point. And there will be quite a few more features that help you understand what's going on with your fuzzing campaign.
So we are going to release all this stuff later?
Yes, so this will also be released in the next few days. There's a link to the GitHub repo already at the last slide. And since we're already at the topic of creating tools, so I think Fuzz is a really great building block to build even better tools. So there's a really great talk by Brett Victor. It's called Up and Down the Ladder of Abstraction, and it talks about understanding systems. And the example system that they have is a little car that's going along a road. And this little car has a very simple route set. If it's already on the road, it just going straight ahead. If it's on the right side of the road, it's steering to the left. And if it's on the left side of the road, there's also a link down here, which unfortunately it's really hard to read, but it's in the slides, so you can look up the original blog post, which I heavily recommend. If it's to the right of the road, it steers left, and the other way around. This car has a single input parameter, and that's how strongly will the steering act. And usually if we want to interact with such a system, and I mean in our case we don't care about cars, we care about complex software, but just to keep the analogy going, we can use a debugger, and the debugger allows us to set a breakpoint and actually inspect the state of a software whenever a breakpoint is hit. And we can inspect individual concrete snapshots at a given time, and restarting is really expensive. So the first thing you can do is you can abstract away time, and in that case you can see all of the time steps of the program at the same time. In the real world of program analysis, that would be debuggers, time-traveling debuggers such as RR. Does anyone know RR? That's nice. I can heavily recommend trying out RR. And if you have, I don't know how much that costs, but more than I can afford, you can also probably try Reven, which seems a pretty cool tool, but I can't afford it. So the next step is abstracting away the inputs. And what does that mean? So in the car example, that means we generate runs for all kinds of parameters. So for all different strengths of steering, we get a bunch of different, so this is really hard to see. These lines actually continue here. So I envy the people in the later rows that can actually look at the monitors. I'm sorry about that. So in this case, we have a bunch of lines that represent all different kinds of car behavior depending on the inputs. And having this data set available, we can now answer a whole bunch of questions very easily. For example, we can say which is the fastest connection, or which is the one that takes the most time to reach the end of the road, or which is the one that actually stays on the damn road. And so what would that look like for real-world software, right? That's not trivial, but I wish I would have managed to finish this demo with my tool, but I didn't because I got ill the last week. And so we will have to fake it. So this is not available just yet. But basically, we have a tool here where some kind of packages are parsed, and we have the input that actually got us there, and we want to understand this input. Now, this is hard to read. I don't know what this does, right? But what we know is the opcode of the package is currently stored in a given register. And what we can do is we can add a watch point that evaluates the value of this register at this time. And then we can rerun experiments. Like we can ask the fuzzer, hey, let's see how flipping bits in this input affects the value of those watch points. And since we can flip a few hundred bits per second, we can perform a completely automatic analysis. And in that case, I envision something where we get a color-coded output. So this means if we change this bytes, then we don't even reach the watch point, so don't touch this. Then we got this one, which means if we change this, this directly affects the value of the watch point. Then we have gray ones, which means, well, this doesn't matter at all. Changing this won't change anything in relation to the watch points. And we have the green ones that affect the number of breakpoints that were actually hit. And using this, we can already see a lot clearer that there's some strong structure to the input format where we have the opcode type in these header fields, and then some length fields, and then some data that we don't care about from the point of view as concerning the headers. So I said this is fake, but there's already a tool like that out there. AFL actually ships with AFL Analyze that does perform some automatic format reverse engineering. It does not allow you to specify exactly which values you're interested in, so it is a lot less precise. But it already does a surprising amount. It can already infer a surprising amount from a file format of about a file format from just looking at the bitmap. Another thing is root cause analysis, which is a research project that we will publish soon, where you find a bug, and then you use your fuzzer to abstract away the exact path of the bug taken. So you fuzz the crash and save all the other crashes that you find and throw away all the non-crashing inputs. And that gives you a large set of non-crashing inputs and a large set of crashing inputs. But you only keep fuzzing the crashing ones. And then you can you can come up with hypotheses automatically that try to predict whether the input will lead to a crash or not. You just generate a large amount of these hypotheses and look at the correlation between the outcome of this hypothesis and whether the thing actually crashed or not. So the best one will hopefully separate all the crashes from all the non-crashes, and all of those are really good indicators of what the actual problem with the bug was. And we used that to identify pretty complex bugs with involved type confusions and just-in-time compilation issues where the just-in-time compiler miscompiled stuff. There's also some pretty cool research by Sean Hallam where the goal is to abstract away different kinds of interaction with the heap. So if you want to build a heap exploit, then you can ask the fuzzer, hey, can you groom the heap for me? I want it to be in this particular shape. Try to make the heap that you actually see look more like the heap that I actually want to have. And that way we can, for example, ask the fuzzer figures out, hey, I can avoid this allocation or make it go to another position, and then we can actually get our allocation in place so that an overflow will actually do something useful. So I think the key takeaways here really are using fuzzers. I think it's quite possible to build a whole bunch of tools that go far beyond just uncovering bugs. They will be able to help you understand what's actually going inside of the program in ways that are really hard to imagine right now. And the last topic I want to talk about is unfuzzable code. So how are you going to fuzz code that doesn't even run? So there's some pretty cool research on that. And the idea is basically, for example, in firmware, you have I/O interactions with real hardware. You don't have access to the hardware. You have too little of the hardware, so you can't really run a fuzzer because the hardware is slow. You don't know it. You just reverse engineer the firmware. For whatever reasons, you're not able to use the software and run it natively. So what you can do with a lot of tricks and a lot of smart engineering is you can actually make the fuzzer interface the firmware and act as the real hardware. So whenever the firmware tries to access some I/O values, the fuzzer is tasked with producing a value. And the fuzzer will try to incrementally make the firmware show more and more interesting behavior. And if you do that, you can actually get a firmware image to boot and to run an HTTPS server, and you can actually run Fuzz HTTP servers inside of the firmware without being able to access the real hardware that would be needed to actually perform network requests, for example. So there's some pretty cool research out there that was recently published, and one of the authors actually is sitting right there. So go talk to him if that sounds cool to you. Key takeaway, fuzzers are really, really powerful if you use them well. And the last thing I want to talk about, because that kind of, that was the kind of research that caused some controversy. We thought maybe you don't want your software to be fuzzed. So how can we prevent software from being fuzzed with modern fuzzers? And there's a whole bunch of things you can do. For example, you can build additional code that basically allows you to take many different paths, and whenever the hash of the input changes, you pick a different path. So maybe it's this one, maybe it's this one. Every time the fuzzer flips a bit in the input, the fuzzer observes a new path, and thus the ability to learn what's actually interesting input and what is not is greatly diminished. Next thing you can do is you make your target slower in the cases that the fuzzer cares about, but not your users. So for example, your users will probably not generate lots and lots of syntactically invalid inputs. And if you do, you can just make the program wait for, I don't know, like 1/10 of a second or something like that. And that already pretty much kills fuzzing, because fuzzing will generate mostly syntactically invalid inputs. And now the assumption that underlines all of fuzzing, that you can get lots and lots of executions per second, is basically gone by adding some delay. You can do something very similar with the signal handler. So if your application crashes, you can just delay the crash for a second, because if your application seg faults, in many scenarios, you don't care if it seg faults now or a second later, but the fuzzer will then have to wait for a whole second to observe the actual crash. If you care about all this fancy stuff, that's even easier to beat. You can just encrypt and decrypt the input once, and all of those symbolic techniques are out of the window immediately. They can't do anything about this. So we built something like this, and it pretty much means, so the baseline here is running the first input, and pretty much all of those fuzzers barely beat running the input within 12 hours. there is some issues with this. So as said, it was causing a bit of a controversy. And the issue here is, basically, if you do this, you will lose access to all whitehead attention. A whitehead will not spend a week removing this anti-fuzzing stuff. A blackhead, on the other hand, might very well be interested in spending a few days to remove your anti-fuzzing and then get the fuzzing results. So you basically trade off all whitehead bug reports ever against delaying your opponent for a few weeks, or a few days even. So that might be a valuable trade-off if you're doing software where you do heavy anti-reverse engineering anyway, and an opponent that is manually analyzing your software is a problem in itself. But someone actually did this for an open source project because he was so annoyed by bugs that some fuzzing people filed that he actually hooked the signal handler, and that did not end well. So that was my idea of a roadmap for future fuzzing research, and I really think that fuzzers are building blocks. Like, we still don't really understand fuzzers that well, but I think they're building blocks for a new generation of tools that we can use to understand software, to validate software, to find bugs in software, and to understand the bugs and exploit the bugs too. So as a conclusion, I would ask you to join me, build better tools, join us, build better tools for future generations of bug triage, or in that case, unearthing bugs if you want. This is the whole set of GitHub links. And this is, oh, sorry. So this will be available, obviously, on the Black Hat slides. And this is our information. And in particular, I would like to thank our collaborators that made all this research possible, that were not here today, but that still did a lot of work in all the papers that we published. And so that's it. Do you?
Yeah, that's it.
So if you have any questions, I think we have like 2 or 3 minutes left. If you can ask quick questions, then that would work. Otherwise, we'll be around here and happily answer your questions after the talk. So any questions? No? Okay, then.
There.
Oh.
Or there.
Microphone is coming.
Yeah.
Hi, thank you for the talk. So I want to ask that what's the difference between the memory snapshot you just proposed against the consistent mode in the current AFL?
Well, if you run something in consistent mode, so you just run the code in a loop. The process does not terminate, right? And just think about it. If there is some kind of statefulness in the process, yeah, then you might not found all bugs, or there are other issues. And by using our approach, it's basically we don't care. So we will always have a new, fresh process, basically a new, fresh virtual machine. And yeah, so there are no stateful issues, no non-determinism, stuff like that. So if you run something with AFL in persistent mode, yeah, in most cases, the stability will just drop.
Yeah, so for example, you might actually trigger a bug, but it doesn't crash. It just corrupts some values. And now, a few thousand inputs later, these changes actually caused the bug. And now you're in a hard time to actually figure out what was the bug, right? Because AFL threw away the input that actually caused the bug, but saves the input that stumbles over the broken state.
Yeah.
And so what we do is a lot more like a fork server than like the persistent mode. So it's basically the complete opposite of the persistent mode. So it's fork server for whole VMs.
So in terms of the fork server, so my next question is, have you ever think about like, can we, rather than just like start the fork server at the beginning, is that possible that we can like choose multiple places?
Yeah, actually I think you can. And lots of this interactive stuff you can probably build using a normal fork server without our technology too.
So like, do you have any like kind of opinion or heuristic for like where can we start another fork server in the program?
For example, you could use I/O interactions.
Yeah. So basically network. So if you don't fuzz something like a file, then you can. So in terms of network communication, you don't know when the communication will terminate. Therefore, you can just create a new fork snapshot after each new package, and this way increase performance and find even more bugs. It really depends on the target. So yeah, I'm not sure if you can give a general answer to this question.
But you like read, for example, like if your application does not read the whole file in one chunk, you might just hook read. Okay, and this is the time. So if you have any more questions, please come to us. We'll stay here for the next few minutes, and then we probably can meet us over tea or coffee outside.